Good morning, dear students, and once again, welcome back to our course. From the last lecture, we started a new portion in the series of GATE classes, that is Prerana scheme. And the course that we have started is control system, because I told you that as far as electrical and electronics communication engineering students are concerned, network theorem and then control system plays a very important role as far as mark distributions are concerned. And in the last lecture we discussed in detail about the fundamental aspect related to system. So what exactly system is? So system is nothing but a combination of different physical components which entirely act as unit to achieve some objective. And every physical object we can treat as a system. For example, classroom, which is a combination of blackboard, chair, table, is a system, and we can classify them like biological and physical system. Now, what is the importance of control in system? Control basically add three different functions simultaneously. First one is direction, second one is regulation, and third one is commanding. That means if a system is control, that means that system is capable to perform direction, that system is capable to perform regulation, and also capable to command itself or some other component available in the system. Now based on that we define the definition for control system. So it is a combination of different physical components which entirely act as unit to direct, to regulate, or to command itself or some other component of the system. And then we discussed the example for control system, and we have taken a very simple example where we have three different components. First one is the source, then second one is the switch, and third one is the bulb or lamp. And all are connected in series configuration, or you can say a voltage source is connected in a closed loop to provide main excitation to the circuit. And this is the example for control system. Why? Because by changing the position of switch, we are in a position to control the state of lamp. When the switch is on, uh, bulb is going to convert electrical energy into light energy, and when the switch is off, the conversion is going to be zero. That means by changing the position of switch, we are in a position to control the state of lamp. And then we discussed the components of control system. So normally, if you consider any physical control system, we have two main components in it. First one is called as plant, and second one is called as controller. Now, what is plant? Plant is the portion of a system whose function is to be controlled. So, with respect to our previous example, bulb or lamp we can treat as a plant, and controller is the element of a system which may be present inside the system, which may not be present inside the system, but its main function is to control the action of plant. That is important. So with respect to our previous case, switch is going to act as a controller. And then we discuss disturbed signal. So disturbance or disturbed signals are nothing but unwanted signal which basically going to affect the performance of the control system. And there are two different types of disturbed signal, internal and external. Then we discussed how to represent the general block diagram of a control system in time domain as well as in frequency domain. So whenever we are dealing with the representation of control system in time domain, normally the signals like reference input signal, which is also called as excitation, or the controlled output signal, which is also called as response, are indicated by small letters followed by t, where t indicate that that particular signal is a function of time, like R of t indicate reference input signal and C of t indicate controlled output signal. Then how to represent the control system in frequency domain? So the same representation is there, but instead of writing small letters, now we are using capital letters followed by S, where S indicate that now the reference input signal and the control output signals are the function of frequency, capital R of S and capital C of S. And then we discuss how to classify control systems. So basically, out of this nine different types of control system. Three are the most important with respect to gate exams are concerned. So time variant, time invariant, then linear, non-linear, and open loop and closed loop control system. So in the last lecture, we discussed in detail about the concept of time variant and time invariant control system, then linear and non-linear control system. So I told you that time variant and time invariant. So this variancy we are going to define with respect to the system parameter. That means if the parameter of systems are going to vary with respect to time, that is called as time variant control system, even though the input and output are not the function of time. Whereas in case of time invariant control system, the system parameters are not going to vary with respect to time, even though input and output are the function of time. So example for time variant is launching of spacecraft or satellite, and example for time invariant systems are nothing but any simple electrical circuit where we have a combination of R, L, C, and once we have designed that circuit, the value of R, L, and C are going to be the constant one, irrespective of the input excitation and the controlled response. Then this figure indicate that how to represent time variant and time invariant control system. And for the ease of calculation, I told you that in general, all type of control systems we are going to consider as time invariant. That means once we have designed that system parameters are not going to change with respect to time. They are going to be constant. But input and the output are the function of time. So this you have to remember. And then we discuss the concept of linear and non-linear control system. So what is linear? A system is said to be linear if it is going to follow superposition principle. And when a system is going to follow superposition principle, that means it has to follow two properties simultaneously. First one is additive and second one is homogeneous. And then we discussed the physical significance of additive property and then homogeneous property. And finally, we have taken a practical example of a resistor, and we identify that whether the resistor is linear or not, and we apply the logic. First we check that whether the resistor is going to obey the property of additiveness, and finally we conclude that resistor follow the property of additiveness, and then we apply the logic of homogeneity just to check whether it is capable to follow homogeneous principle or not, and finally we conclude that resistor is obeying homogeneity property. So we can finally conclude that resistor obey superposition principle, hence a resistor is linear in nature. And to have ease in calculations, finally we conclude that all physical systems we are going to consider to be a linear control system. In the previous case, I told you that by default we are going to take control systems as time invariant, and here we are going to take control systems as linear one. So by default, if you combine these two statements, we can write that linear time invariant control systems are the main systems that we are going to consider in the coming session as far as gate syllabus is concerned. Now, in this particular lecture, we are going to start first the concept of open loop and closed loop control system, because this is the only classification which is left under the domain of different types of control system. So first we will cover this particular point where we discussed in detail about the concept of open loop control system, closed loop control system, what are the significance of open loop, what are the significance of closed loop, what are the demerits of open loop and closed loop control system, how to represent in general a open loop control system, what are the fundamental components available in open loop and closed loop control system, and finally we are also going to make a comparative analysis between open loop and closed loop control system. And then in the second portion of this lecture, we are going to discuss the fundamental aspect related to mathematical modeling of a control system. For example, if you have a control system, how to find out its mathematical modeling, what is the concept of translatory motion type mechanical system, and what is the concept of rotational motion type mechanical system, and what are the fundamental components available in translatory motion type and rotational motion type mechanical system, and how to find out their mathematical modeling. So first, what is open loop control system? Now see here, it is a type of a control system in which the output of a system depends on input, but change in input does not going to have any control on the output. What is the meaning of this? Now see here. So what is open loop control system? It is a type of a system in which the output of a system depends on the input, but input does not depends on the output or change in output. This is very important. That means if you have a system like this, and if you apply some kind of excitation to that particular system in the form of input like r of t, so corresponding to that, this is going to generate some output which is nothing but c of t. Now from this system it is very clear that this is control system cs. Now from this system it is very clear that if you change the input, corresponding to change in input, output is going to vary. For example, instead of supplying r of t, if you vary this to r1 of t, so corresponding to that, it is going to generate some new output which is nothing but c1 of t. In the same way, if you vary this particular input from r1 of t to say r2 of t, so corresponding to this, it is going to generate some different output which is going to be c2 of t. So from this it is very clear that output depends on input, but input does not depends on output or change in output. For example, if you due to some reason, due to some error, or you can say due to some disturbed signal, if the system is not going to generate the required output, then in that case input is not going to vary. Input is always going to remain the same, which we applied in the form of excitation to this particular system. So that type of systems are called as open loop system or open loop control system. So finally, what is open loop control system? It is a type of a system in which output depends on input, but input does not depends on output or change in output. So such type of systems are called as open loop control system. And how to represent open loop control system? So as I told you that if you take any control system, any physical control system, in general, we have two main components available in it. First one is called as plant, and second one is called as controller. What is the purpose of plant? Plant is the portion of a system whose function is to be controlled. And what is the purpose of controller? Controller is nothing but the element of a system whose function is to control the action of plant. Apart from that, to this controller we applied some reference input, which is nothing but the excitation indicated by symbol r of t. So when we apply some reference input to the controller, it is going to generate some signal. So this is called as actuating signal. So actuating signals are nothing but the output of controller, which is provided as an input to the plant, or you can say the processor. And finally, based on the actuating signal, the plant is going to generate some response that is called as controlled output indicated by symbol c of t. So this is the general representation of open loop control system. So here if you vary this reference input signal, corresponding to that control output signal is also going to vary. But if this control output signal is vary due to some disturbances or due to some error signal in the system, the input is not going to change according to that. The input is always going to be a constant one, because here we don't have the concept of feedback loop. So input is not able to sense what are the changes which are going to happen over the output side, and hence the system is called as open loop control system. What are the advantages for open loop control system? Advantages are: number one, designing is very easy. Then it is easy to construct, because it is easy to construct, hence the cost is low. Maintenance is low, and the open loop systems are highly stable in nature. Why? Because there is no sensing mechanism, there is no feedback loop available in open loop control system, because of which the input is going to vary. The input is always going to be constant one, irrespective of the variation in output. The input is always going to be a fixed value. So these are the advantages of open loop control system. Now let us try to identify what are the disadvantages. Number one, it is unreliable and inaccurate. Why it is unreliable and inaccurate? Because see, suppose if you have a system and we design this particular system for some objective. For example, if you apply some input to this, based on this the system must generate some output, which is nothing but C of t. So this C of t indicate its desired output. Desired output. Now due to some reason, for example due to some disturbed signal which is developed in the system itself, and I told you that disturbed signals are basically affect the performance of a control system. So instead of generating C of t, now this particular system is going to generate C1 of t. And suppose if you are interested to calculate the error signal, which is going to be E of t, so it is going to be equals to what? C of t minus C1 of t, or you can write C1 of t minus C of t. Now because this particular system does not have the capability to sense what are the changes which are going to be happen on the response side, based on that we are not in a position to manipulate the input signal, because the variation in output are not going to affect the magnitude which we have provided in the form of excitation to this particular system. And hence depending upon the disturbance signals which are created inside the system, or maybe due to some external sources, the output is not going to be achieved, or you can say desired output is not going to achieve. That leads to create error in the system. And because this system is not capable to sense the change in output, and based on that it is not capable to change the magnitude of input excitation, the error remain in the system. Hence the systems are unreliable and they are inaccurate. Then does not sense the environmental changes, as I told you that they are not capable to sense the disturbed signal. Does not sense the internal disturbances. Examples for open loop control systems are nothing but washing machine, and then traffic signal, and then toaster are nothing but the examples for open loop control system. Now normal washing machine basic objective is to wash cloth. If we have a piece of cloth and suppose here we have a dirt, then we need to add water, we need to add some washing powder in that machine, and then we need to turn on the machine. It will try to rotate and try to wash and try to clean this dirt mechanism. Now if the system is open loop, irrespective of whether the dirt is completely removed from the cloth or not, the machine will stop functioning after the predefined duration. For example, if we start this washing machine for say 5 minutes, so irrespective whether the dirt is clean or not, the machine automatically stop after 5 minutes. That means the input to the machine is not going to change with respect to change in output. For example, if the system is a closed loop instead of open loop, now depending upon this dirt mechanism, this machine automatically going to decide for how much duration of time, by what rate, how much amount of washing powder we need to take from the supply, so that we can completely remove this particular dirt from the cloth. So hence, if the machine is fully automated, then in that case we can treat that particular system as closed loop. But because the machine is not fully automated, it is a kind of open loop system where we need to define all the parameters initially, and once the defined parameters get over, the system stop working, irrespective whether the objective is achieved or not. In the same way, traffic signal we can treat as an open loop control system. Why? Because suppose here we have a traffic signal structure like this, and there will be a flow of traffic from this particular point to this particular point based on the signal mentioned over here. Now, after every 60 seconds, or you can say 1 minute delay, the switching pulses are set over here. So, starting from this particular point, the traffic will move from A to B, and then after 60 second of span, this traffic will move from B to C, and then after 60 second of span, this traffic will move from C to D, and then from D to A after 60 second of duration. Now suppose this system is a closed loop. Now what will happen, due to some reason, if there is a inconveniency which is going to be happen over here, maybe some sort of accident is occur over this particular point. Now what we need to do, because the system is now in open loop mechanism. So irrespective of the disturbances which are occurring in the system, the traffic signals are switching by the rate of 60 seconds only. दैट मीन्स उन्हें कोई लेना देना नहीं है कि यहाँ पर आपका फॉल्ट आया है कि नहीं आया, मतलब यहाँ पर एक्सीडेंट हुआ है नहीं हुआ है, वो हमेशा 60 सेकंड के पल्स से ये जो सिग्नल्स है उनको क्लॉकवाइज सेंस में या फिर एंटी क्लॉकवाइज सेंस में हमेशा कंट्रोल करते रहेगा. बट अगर इफ दिस पर्टिकुलर सिस्टम इज क्लोज लूप टाइप, then in that case what is going to be there? If first of all from image processing or from real time data, it is going to take the actual scenario of the situation, and when the system identify that there is a problem at the location, might be some kind of accidents are happening over there, and because of that reason this particular system will stop. Might be possible that it is completely stopped depending upon the severity, or it may possible that it is going to increase this delay. So instead of taking 60-second a delay, it may possible that it increases to 120 second, or it may possible that it increases to 180 second. And even though the traffic is not get cleared, the system get completely stopped. That means the output of the system depends on input, but at the same time, if there is a variation, you can say, in the output, then corresponding to that input is also going to vary its value. That means that is the example for a closed loop control system. So closed loop control systems are quite intelligent as compared to the open loop control system. Open loop control system does not have any intelligence, but closed loop control systems have an intelligence because their output depends on input, as well as if there are changes in the output, corresponding that the input is also going to vary. That is important. Now, what is closed loop control system? Now, in this type of control system, see here, output depends on input, but we can say that if the output is going to vary, corresponding to that, the input is also going to vary. That is important. For example, if you have a system like this, and to that you apply some input in the form of R of t, corresponding to that is going to generate some controlled output C of t. So here output depends on input. But if due to some reason this output is going to vary, then corresponding to that this input is also going to vary so that it can achieve a desired output. That is what closed loop control system. And just for this reason, because now in this case, depending upon the change in output, the input is also going to vary. So hence, at real time scenario, the change in output has to be sensed by this particular system. So there will be a feedback loop in between output and the input. This is very important. So in case of closed loop control system, there is always a feedback loop. And what is the objective of using feedback loop? Just to sense the changes in output, and corresponding to the change in output, input has to vary. Now this indicate the general representation of a closed loop control system. Now here, if you see the main system, as I told you that if you take any physical control system, basically we have two components in it. First one is called as the plant. Second one is called as the controller. Apart from that, there are some more components available in closed loop control system, like we have transducer. Transducers are basically in a kind of device that is basically going to convert the physical signal into electrical pulse. So here we have some command input, maybe in the form of temperature, maybe in the form of distance, or maybe in the form of any physical signal. So here we have physical signal that is converted into the electrical pulse, or you can say electrical signal, with the help of transducer. So this R of t is going to act as a main input to the system. Then we have this summing block, and the main objective of the summing block is to generate the error signal, this error signal. So this E of t indicate the error signal, and this error signal is provided as an input to the controller, and it is going to generate some actuating signal as an output, which is nothing but U of t. Now this actuating signal is provided as an input to the plant, and it is going to generate final output in the form of response, that is nothing but controlled output. And because now this is nothing but a closed loop control system, and it has an ability to sense the changes in the output, that's why I need to provide some feedback mechanism. So this is nothing but the feedback path. and here we have some element which are considered to be the feedback element, and this feedback path is going to generate some signal. So this b of t indicate your feedback signal. So this is nothing but the feedback signal. And if you see the summing here, the summer is provided two different kinds of signal as an input. First one is the reference input signal, which is nothing but r of t, and second one is the feedback signal. Now, depending upon the sense of feedback signal, we may take this as positive, we may take this as negative. We can have two different types of feedback mechanism: positive feedback mechanism and negative feedback mechanism. And based on that, this summary is going to generate some output, which is nothing but error signal. So mathematically, we can write this error signal E of t is going to be equal to the combination of R of t plus minus B of t, where R of t is the reference input signal, B of t is nothing but a feedback path signal, and this is nothing but R of signal, where R of which is where this E of t is nothing but the error signal, and the value of these error signals are adjusted, or the value of this error signal is provided as an input to the controller, and based on the control algorithm which we have implemented over here, the controller is going to generate some kind of actuating signal, so that this actuating signal is provided as an input to the plant. Hence it is going to generate a kind of controlled output based on which b of t is going to vary, and hence the error is going to vary. So ultimately our objective is, if the signals if the system is running smoothly, then in that case this c of t is going to be equal to the desired controlled output. Then in that case the value of this error signal is going to be 0. The moment we have some kind of disturbances, maybe due to internal source, maybe due to external source, the value of c of t is now going to change to c1 of t. Now based on this, the feedback path is provided as an input to the summer block. Based on that, it is going to generate some error signal. Now in this case, error signal is not going to 0, it has some finite value. Now this error signal is provided as an input to the controller, and the controller is going to generate actuating signal as an output. Now the value of this actuating signal is in such a way that it will force the plant to generate the desired value. That means instead of generating c1 of t, now the actuating signal which are produced by the controller is in such a way that it is going to generate c of t instead of c1 of t. And the moment we have c of t output, again the error signal is going to be 0. So in this way, this closed loop mechanism is continuously working. So the same thing is mentioned over here. The thing is that you have to remember these representations very accurately, because these are all standard representations, and from this time onwards, throughout the completion of this course, we are going to use these representations for different kind of signal. For example, reference input signals are indicated by symbol R of t, error signals are indicated by symbol E of t, then actuating signals are indicated by symbol U of t. They are also called as manipulated signal. Then control output or response is C of t, and feedback path signals are P of t. And finally, we can write the relationship between reference input signal and feedback signal, like error signal is nothing but R of t plus minus B of t. So when to take plus, when to take minus, that depends upon the sense of feedback path. If we are dealing with negative feedback signal, the error signal is going to be like R of t minus B of t. If we are dealing with positive feedback signal, it is going to be like R of t plus B of t. So these points you have to remember. And the actuating signal are generated in such way that the error signal is always going to be 0. So that is what our final objective is. We want to minimize error signal so that the system is always going to generate the desired output for which it is designed. What are the advantages and disadvantages of control system, that too closed loop? So what are the disadvantages of open loop control systems? All are take care in the form of advantages in closed loop control system. Number one, it is accurate and reliable. Then it senses the external changes in the environmental condition. And number three, it senses the internal disturbances in the system. Now what are the disadvantages? Number one, designing is more complicated, hence cost effective, or they are highly costly. Then stability is the major issue in case of closed loop control system. That is very important. Now, let us try to understand the comparative analysis of open loop and closed loop control system. So, on first column we deal with open loop, and on second column we deal with closed loop control system. In case of open loop control system, the input does not depends on output or change in output, but in closed loop control system, input depends on output or change in output. Here, no output calculations are required because it is open loop, but in case of closed loop control system, output calculations are required, and at each and every time we need to calculate the value of output. If the output is exactly going to be equal to desired output, the error signal is going to be 0. But if in case due to some disturbances, maybe internal or external, if the output is not exactly going to be equal to the desired value, then in that case error signals comes in picture, that is provided as an input to the controller that generate actuating signal, just to make the output generated by plant exactly going to be equal to the desired output. In open loop control system, there is no feedback mechanism because there is no sensors. In case of closed loop control system, yes, there are feedback mechanism. It may be positive or it may be negative. Then open loop control systems are stable, and here they are not stable because stability is the major issue. Why? Because here we are sensing the disturbances, and if disturbances are there, they are leads to affect the performance of system. Hence, they are going to affect the stability of the system. Error detector is completely absent in case of open loop control system. Here, error detectors are present in closed loop control system. And cost is low because the system is not so complicated. Here, cost is high. Designing and constructions are easy as far as open loop systems are concerned, but as far as closed loop control systems are concerned, their designing and constructions are complicated, difficult. Maintenance is low, here maintenance is high. And this is the pictorial representation for open loop control system. So basically we have a control system, and if you open this control system, inside this control system we have a combination of controller followed by plant, and to this we provide some input in the form of excitation, that is R of t, and it is going to generate some controlled output in the form of C of t, and this is nothing but your linear time invariant linear time invariant control system. This is very important, and this you have to remember. I already told you that whenever we are dealing with control system, as far as gate is concerned, we have by default linear time invariant control system, and this is the representations for closed loop control system. So we have controller and plant which are present inside the control system. So if you open this control system, here we have a combination of controller followed by the plant, and to this we apply the main reference input R of t, followed by this it is going to generate some controlled output signal C of t, and then we have a feedback path element, and then depending upon whether we have taken positive feedback, whether we have taken negative feedback, we have a feedback element, that is P of t, and then based on that it is going to generate error signal, that is nothing but E of t. And the relationship between error signal with respect to reference signal and feedback signal is R of t plus minus B of t. This is very important. So this is what about open loop and closed loop control system. What is the significance of open loop? What is the significance of closed loop control system? Their advantages, disadvantages, and finally the comparative analysis between open loop and closed loop control system. Now we are going to start the another portion of our topic that deals with the concept of mathematical modeling of a system. Now, what is mathematical modeling and how we can do mathematical modeling for a system, that we are going to cover. So, mathematical modeling of a system means what? It is simply the representation of a system by means of some kind of mathematical equation. For example, if you have a system, okay, and you want to represent this particular system by using some sets of mathematical equation. So finally, the set of mathematical equations through which we are in a position to define the behavior of this particular system may be a static behavior or it may be a dynamic behavior. Then that representation of a system in the form of mathematical equations are called as mathematical modeling. That is important. So mathematical modeling मतलब क्या कि सिस्टम आपके पास में अवेलेबल है, फिजिकल सिस्टम आपके पास में अवेलेबल है, और आपको वो पर्टिकुलर सिस्टम को रिप्रेजेंट करना है बाय यूजिंग सम सेट ऑफ मैथमेटिकल इक्वेशंस. इट मे बी लीनियर इक्वेशन, इट मे बी डिफरेंशियल इक्वेशन, इट मे बी इंटीग्रो डिफरेंशियल इक्वेशन. Ultimately you are ending with some set of mathematical equations, and the equations are written in such a way that if you solve those equations, we can easily find out the static and dynamic behavior of a given system. Then we can say that the mathematical modeling of the system which we have done is correct or for the given system. So in mathematical modeling, each component of the system is going to represent by its own differential equation or by some set of equations. And if a system is consist of n number of physical component, then for each component we have some kind of equation. So we have n set of differential equations or n set of mathematical equations. And mathematical modeling of system means representation of a system by means of a set of equations through which we are in a position to define static as well as dynamic behavior of the system. That is very important. And based on the type of system, we have different approaches to find out the mathematical modeling of a system. For example, for mathematical modeling, normally we can deal with two different types of system. First one is called as electrical system, and second one is called as mechanical system. So here we have two different types of system. First one is called as electrical system, and second one is called as mechanical system. Mechanical system. And in mechanical system, depending upon the nature of motion, whether we are dealing with linear motion or whether we are dealing with angular motion, we have two different types of mechanical system. First one is called as translatory motion type mechanical system, and second one is called as rotational motion type mechanical system. So in translatory motion type mechanical system, we are dealing with linear motions. So here we have force, here we have mass, here we have linear displacement, and so on. But in case of rotational motion type mechanical system, we are dealing with uh, a kind of angular motion. So here we have angular velocity, angular velocity followed by torque followed by inertia. So instead of writing force, we are having torque. Instead of having mass, here we have inertia. So based on the kind of physical system which we are having with us, we can bifurcate the types of system into two domain. First one is electrical and second one is mechanical. And then in mechanical, again, we have two more bifurcation. If we are dealing with linear kind of motion, then we are basically dealing with translatory motion type mechanical system. And if we are dealing with rotational motion type mechanical system, where we have the concept of angular velocity followed by torque and inertia. So there are different approaches to find out the mathematical modeling for different types of mechanical system, and steps that are involved in the modeling of a system. So first of all, we need to identify that whether the system is mechanical or electrical. Once we identify that the system is mechanical or say electrical, then in mechanical again we are having two different domain, translatory or you can say rotational. And then we need to identify the number of displacements available in the mechanical system. Then each particular what we can say displacement is treated as a separate node, so we need to draw the node diagram. And to draw node diagram, we need to apply this logic that number of nodes available in node diagram are going to be number of displacement plus 1. Then we need to apply the condition at equilibrium, and finally we need to write the equations of force or you can say torque corresponding to the type of mechanical system available with us. For example, if we are dealing with translatory motion type mechanical system, we need to write the equation of force at equilibrium condition. In the same way, if we are dealing with rotational motion type mechanical system, we need to write equation of torque at equilibrium condition. And then we need to apply Laplace transform to convert that into frequency domain. Then we are having two different topology to find its analogous quantity. So analogous quantity means what? If you are having a mechanical system, and if you want to convert that into electrical system. So here in mechanical system we have mass, we have force, we have say displacement. Here we have damping coefficient, then spring constant. So these mechanical components we are trying to represent into their equivalent electrical component, like resistor, then inductor, then capacitor, then voltage, then current, then flux, then you can say charges and all. So how to convert this uh, various component of mechanical system into analogous electrical component? For that we are having two different topology. First one is called as force voltage topology, and second one is called as force current topology. And once we have the representation of a system into their analogous electrical parameter, then we need to draw the circuit diagram. So this is what the process that we need to implement in order to find out the mathematical modeling of a control system. But as far as the time durations are concerned, I'm not going to cover this particular portion in detail. I just want to explain you the fundamental aspect of mathematical modeling and how mathematical modeling is going to be done. Because as far as gate is concerned, this portion is not so important, because in gate the questions were asked on transfer function, the questions were asked on time response analysis of control system, questions were asked on frequency response analysis of a control system. But due to the portion, uh, I'm going to cover some important aspect related to mathematical modeling. That means if you have a mechanical system or if you have an electrical system, how to find its corresponding mathematical representation. So that basic concept I'm going to consider, and then in the next lecture we will switch to very important topic of control system, which is very much important as far as gate is concerned, and that is nothing but the concept of transfer function and how to find transfer function if the system is given to us, maybe in the form of mathematical equations or maybe in the form of some physical representations. So suppose if you have a electrical system, and your objective is to find uh, the mathematical modeling of that electrical system. How to find out? Ultimately we need to apply some KVL, KCL or network theorem concept to find out its mathematical modeling. For example, if we have resistor like this is say R1 and this is say R2, and to this we apply some voltage in the form of excitation. This is going to be V. So this is plus, this is minus, potential difference is available, path is closed. So definitely we are having a current flowing through the circuit, that is nothing but say I. And we know that current always flows from higher potential to lower potential. So this is going to be plus, this is going to be minus, this is going to be V1. Again the same current is flowing through resistor R2, so this is going to be plus, this is minus, and this is going to be V2. So this is what the system is known to us, and our objective is to find its mathematical modeling. Mathematical modeling. So how to find out? Now see here, if you apply Kirchhoff's voltage law to this particular equation, I can write this as V, which is going to be equals to, or V, because I am reading the circuit in the clockwise sense, so negative positive, I am going to experience a rise, so it is going to be plus V, then minus, this is going to be what uh, I into R1, and then again going to be minus I into R2, that is going to be equals to what, 0. Or I can write this equation as V is going to be equals to what, I into R1 plus I into R2. Or I can write this as V is going to be equals to what, I in bracket R1 plus R2. So from this equation it is very clear that in the circuit we have passive element, and that passive elements are nothing but resistor, number one, and number two, all the resistors are connected in series configuration. Why? Because same value of current is flowing through R1 and the same value of current is flowing through R2, and this is possible only when these two resistors or these two elements are connected in series configuration. And to this series configuration we applied a voltage capital V. That means mathematical equation through this mathematical equation we are in a position to identify the structure of the circuit, how the circuit is going to be look like, whether it has resistor, whether it has inductor, or it has capacitor. Then if it has resistor, how the resistors are connected, whether they are connected in series or parallel or star or delta, and what is the value of current flowing through each and every element. So I can say that through this equation we are in a position to define the behavior of the circuit. Hence, these equations are called as mathematical representation for this particular circuit. So ये circuit draw करना क्या या उसके against में ये mathematical equation लिखना क्या, एक ही बात है. So this is what the basic philosophy behind mathematical modeling. Mathematical modeling of electrical system is very simple. That means we need to apply KVL, KCL, Ohm's law, some network theorem to find out the representation of that particular system into its corresponding mathematical equation. I hope this point is clear to everyone. Now, suppose we have mechanical system. How to find or how to represent the mathematical modeling of mechanical system? Now, as I told you that in case of mechanical system, depending upon the motion, whether we are dealing with linear or angular, we have two different types of mechanical system. First one is called as translatory motion type mechanical system, and second one is called as rotational motion type mechanical system. So in case of translatory motion type mechanical system, here we have the concept of force. So these are the fundamental operating components available in any translatory motion type mechanical system. Number one, we have force. Number two, we have mass, force indicated by symbol F. Then we have mass indicated by symbol M. Then we have damping coefficient, damping coefficient or friction coefficient. They are nothing but the same thing, indicated by symbol B. Then here we have spring constant, spring constant indicated by symbol K. And then here we have linear velocity indicated, linear displacement first and then linear velocity. So here we have linear velocity, linear displacement. So here we have linear displacement indicated by symbol X, and then we have linear velocity indicated by symbol V, which is going to be equals to dx by dt. In the same way, in case of rotational, here we have torque indicated by symbol T. So instead of force, here we have torque. Then in this case, instead of having mass, here we have inertia indicated by symbol J. Then here again we have damping coefficient B, same. Again here we have spring constant K in the same. Then here instead of having linear displacement, now here we are having angular displacement indicated by symbol theta. And then here we have angular velocity indicated by symbol say omega, and the value is d theta by dt. So these are the fundamental operating components which are available in any mechanical system. If it is translatory, so it is going to have force, mass, damping coefficient, spring constant, linear displacement followed by linear velocity. And suppose if you are dealing with rotational motion type mechanical system, so here we are having torque, inertia, damping coefficient, spring constant, angular velocity, and then angular displacement. So this is very important. Now, because I told you that if we are interested to find out its mathematical modeling, so we should know what is the force equivalent component corresponding to mass, corresponding to damping coefficient, corresponding to uh, spring constant in case of translatory motion type mechanical system. In the same way, if we are dealing with rotational motion type mechanical system, we should know what is the torque equivalent component offered by inertia, offered by damping coefficient, offered by spring constant. And once we know the force equivalent component or torque equivalent component of each one of the fundamental operating component, we can easily write the mathematical equation at equilibrium condition corresponding to force in case of translatory motion type mechanical system, or corresponding to torque in case of rotational motion type mechanical system. So let me tell you that how to write the equations. So I'm writing here equations of force in case of translatory motion type mechanical system. So here we have three fundamental components which plays an important role. First one is your mass. So the force component offered by mass is indicated by symbol Fm, and it is going to be equals to what? M d2x by dt square. That is very important, because from Newton force of equation we know that F is nothing but m into a, where a is acceleration. So I can write here as m into dv by dt, or I can write this equation in terms of displacement as m d2x by dt square. So same equation is written over here. So this indicates the force component offered by mass in case of translatory motion type mechanical system. In the same way, force component offered by friction or damping coefficient indicated by symbol B. It is given by F capital B is going to be equals to what? B times dx by dt. This is very important. This is dx by dt. In the same way, we have spring constant. Spring constant indicated by symbol K. So the force component offered by spring constant, it is given by Fk is going to be equals to K times of x. So these representations, or you can say force component offered by each component in case of translatory motion type mechanical system. That means what is the force component offered by mass, force component offered by damping coefficient, force component offered by spring constant, that you must remember. And then if you apply the condition of equilibrium, I can write here as input force is going to be equals to what? Output force. So input force, consider that it is going to be F. Then output force are nothing but the force distribution in mass, in damping coefficient, and then in spring constant. So I can write here as Fm plus Fb plus Fk. This is very important. So this is the equation of force at equilibrium condition in case of translatory motion type mechanical system. The same logic we can apply in case of rotational motion type mechanical system. So how to write that? So let me erase this. Now here we are having rotational motion type mechanical system. And in rotational motion type mechanical system, instead of having mass, now here we are having inertia indicated by symbol J. And the torque component offered by inertia is given by tau suffix j, because it is torque component offered by inertia is given by, it is nothing but j times d2 theta by dt square. Now instead of having linear velocity or linear displacement in case of translatory motion, now in case of rotational motion we have angular displacement. That's why we have written here theta instead of mass. In case of translatory motion, here we have inertia, that's why we have written j. That you have to remember. That's it. Then second is, here we have again friction coefficient or damping coefficient indicated by symbol B. So the torque component offered by this component is given by T suffix B, and it is going to be equals to what? B times d theta by dt. In the same way, here we have spring constant indicated by symbol again K, and the torque component offered by spring constant is given by tau or T suffix K is going to be equals to what? K times of theta. This is very important. And then we need to apply the equilibrium condition. So if you apply equilibrium equation, input torque is going to be equals to what? Output torque. So what is input torque? Let us consider that it is indicated by symbol T. So this input torque is going to distribute across different types of fundamental components connected in that rotational motion type mechanical system. So it may possible that we may have inertia, we may have spring, we may have damping coefficient. So based on that, this input torque is going to be equals to the distribution of torque across inertia, then across damping coefficient, then across spring constant. Or I can write this equation as T is going to be equals to what? J times d2 theta by dt square plus B times d theta by dt plus K times theta. So this equation indicate the mathematical modeling of rotational motion type mechanical system. This is very general. It is not at all necessary that in a mechanical system always you have all the three components. It totally depends upon what type of structure available with us. Suppose if in a mechanical system we have a combination of inertia followed by spring constant only, then we need to take those two components only. If we have a combination of inertia followed by mm, friction, then in that case we need to take those two components only. The same topology is applicable for translated in motion type mechanical system. The thing is that just like in case of electrical circuit we have RLC, in the same way, in case of mechanical system, maybe translatory or you can say rotational one, we have the logic of inertia followed by damping coefficient or spring coefficient and damping coefficient or friction coefficient, and then we have spring constant. Like in case of translated motion, we have mass, force, and spring constant. In case of rotational motion, we have inertia, then friction coefficient B, and then spring constant K. So this is what the basic philosophy behind the mathematical modeling of a system. It may be electrical one or it may be mechanical one. I hope this point is clear to everyone. So today we will stop at this particular point. In the next lecture, we are going to start one of the most important topic of control system that deals with the fundamental aspect of transfer function. That topic is going to be very important because that is the base for the remaining classes that I'm going to take in this particular course. So you should know what is transfer function, what is the importance of transfer function, how to represent transfer function for any general system. And there we also going to discuss the concept of poles and zeros and how to represent poles and zeros on the S plane. And we are also going to discuss how to find the transfer function of a system if the systems are represented in the form of mathematical equations. For example, if the system is represented in the form of differential equation, how to find its corresponding uh, transfer function. That portion we are going to cover in the next topic or next lecture. Thank you.